Hi everybody, this is Mr. Tubbs, and I wanted to show you guys how do you do one of these gas calculations when two or more variables are changed, okay? Well, you're going to want a couple things to do this. You're going to want a piece of paper, you're going to want a calculator, and you're going to want a writing utensil of some kind. This is definitely not something you want to try to do in your head. So the first thing you want to do is you want to write out your own, I call them IFE charts, but they look a little like this. You're going to have a P for pressure, you're going to have a V for volume, you're going to have a T for temperature, and you're going to have a lowercase n for number of particles. And then the reason I call them an IFE table is you're also going to have an I, which stands for initial. You're going to have an F that stands for final, and you're going to have an E that stands for the effect. Like, what will the change that we noticed affect the gas, okay, or how will it? That's terrible English. So anyways, here's how you fill something like this out. I actually do like to take the time to actually give it a box just so you don't goof up and put something where you shouldn't, okay? But what you want to do is you want to fill out what you know, what is the initial state of the gas. So before the change happens, what do we know about the gas? It says, what would the final volume be if a vessel originally 25 liters at 10,000 millimeters of mercury and 25 degrees Celsius was decompressed to room temperature and cooled to negative 10 degrees Celsius? Okay, so let's fill in what the initial state is. It was originally 25 liters. That is a unit of volume, so I'm going to write that down, 25 liters. It was originally 10,000 millimeters of mercury. That is a unit of pressure, so I'm going to write it down as such, okay? And then the temperature was originally 25 degrees Celsius. Now, before you go and you write that down, we have to understand that degrees Celsius is a flawed unit of measurement because there are temperatures lower than zero. Basically, when you double the temperature in degrees Celsius, that doesn't mean that the amount of energy has doubled in the system, so it's not a good unit for us. The unit that we like to use is Kelvin, and luckily it's super easy to convert from Celsius to Kelvin. All you have to do is add 273, and when you get to college they might make you do 273.15, but I've found that 273 is good enough for us. So when I add those guys together, I wind up getting 298. And then your new unit is Kelvin. And one thing you notice is there's no degree symbol with Kelvin, and that's because it's an absolute unit. So that can go right there. It doesn't mention number of particles ever in this problem. That means the number of particles never changed, and if the number of particles never changed, we don't care about them because they're not going to affect our final volume. All right, the next thing we need to fill out is the final category. So again, I know you probably filled this out when we just changed one variable, but let's fill in what we know. It was decompressed to room temperature, room pressure, and I would share you in one of these problems. Room pressure is approximately 1 atmosphere or 760 millimeters of mercury, okay? So really we would call it standard pressure. So 760 millimeters of mercury is our final pressure. For volume, again, that's the whole point of the problem. I don't know what the final volume is yet. And then the final temperature is negative 10 degrees Celsius. Again, Celsius is no good, so we convert to Kelvin. I get 200 and 63 Kelvin as the final temperature. We're almost ready to start calculating. Now, what I want to do, and different teachers might use this effect row differently, but the way I want us to think about this is I want us to say, hey, the pressure went down. How would that affect the volume? Okay. And from previous lessons, I wanted you to learn, um, what kind of relationships are direct and what kind of relationships are inverse. And it turns out as pressure decreases, volume should be increasing. Okay. And that's basically just because pressure is caused by particle collisions. And one way to lower pressure is to spread all the particles out. Well, if the particles are more spread out, that means that the volume has increased. Okay. So even though the pressure went down, I put an up arrow here because it's going to increase the volume. Now I look over at the temperature one. The temperature went down, and I want to know what is the relationship between volume and temperature. Well, when temperature goes down, volume goes down. This is a direct relationship, so I would put a down arrow there. Just as a little cheat sheet off to the side, I might say, hey, pressure and volume are inverse, and then everything else are direct. So volume and temperature are direct. Pressure and number of particles are direct. And then finally, temperature and volume are direct. Okay? Well, anyways, we've got everything that we need to know. Now we can finally do math. The first thing I would write down is the thing that I'm looking for as a unit. So I would say 25 liters, okay? And with 25 liters, I would multiply that guy by my first ratio. I've got my pressure here, and I'm saying that the volume should go up. Now, in order for these two numbers to make the volume go up, I'm going to need the bigger number on top. And the smaller number on top, or sorry, on bottom. And you can see here, this fraction has a value greater than 1, so when I multiply 25 liters by it, that would result in the volume going up. Now I'm going to do a second calculation with temperature. These two variables are separate from each other, and just because this one says it should go up doesn't mean the temperature has to need to agree. So in this case it disagrees. I don't care. I'm just going to write down exactly what temperature told me. Temperature is telling me that volume should go down, so I'm going to have the smaller number on top and the bigger number on bottom. This fraction has a value of less than 1, okay, which would cause my volume to go down. Now I actually have to do the math to find out kind of who wins. Millimeters of mercury cancel out, Kelvin cancels out, the only unit that's left is liters. So I would say 25 times 10,000 divided by 760 times 263 divided by 298. And I wind up getting a final volume of 290.3 liters. Okay? Well, I hope this helped you all. Make sure that you reach out to us if you have any other questions, and have a great rest of your week.